And the matrix that I see there is just a 1001. Now for this matrix, or those two quadrants, we've got a 2, 3, and a multiple of 2 and a multiple of 3. It's the same multiple. So what we will have is 1 in that place, and 3 times that in the lower left quadrant. And we will have 2. Right. Does everyone agree? Make sense? Okay. And of course, here the zeros are helping a lot. It's very easy to do these additions. It might not always be that way. It might be that you actually really have to add entry-wise. In this case, because all of the zeros, when you add entry-wise, you're just going to add the different quadrants separately. But of course, it doesn't have to be that nice. We can obscure it a little bit. All right. Is this the only way to write this matrix as a sum of Kronecker products? Some other options? Any suggestion? How would you do it differently? And if you don't want to answer, that's fine. There is an answer over there. I'm sorry for picking on you.
I'm not sure if it's right.
What do you suggest?
The top left and the bottom right
Yes?
are separated by a capital link to 1.
Right. So I could do, for example, -1 here, but then I have to do a -1 here. Okay. I can take it a bit further, right? So I could make this 3 if I want, as long as this is 1 over 3. Right, so I can push around constants however I like. I have infinitely many choices. As it happens, this is still not unique. We can find more complicated examples of these two matrices so that the sum still gives us the right result, but start mixing part of this matrix with this one, and start mixing part of this matrix with that one, and we can still get to the same matrix. If you're not careful, then you end up with more terms than are necessary. So I guaranteed that one term is not possible here. We found 2 terms, so 2 terms is enough. We could do it with more. So for example, I could add another Kronecker product and subtract it. That would give me a net result of 0, but it would be more terms in the representation. So what is the minimum number of terms for this matrix? It's 2. So this matrix has tensor rank 2. So the tensor rank is the number of terms that you need there. But I didn't say that very carefully. Remember, I told you if this is 1 by 1 and 4 by 4, the whole thing becomes trivial. So if it's 1 by 1 here and 4 by 4 there, then the tensor rank would be 1. But if it's 2 by 2 and 2 by 2, then the tensor rank is 2. So the tensor rank depends on how you want to divide up your matrix. So you have to decide the structure and then look at the tensor rank. Right. Yes, I probably went far too long.
Okay, I'm sure you probably have a lot more questions, but if you do have, I can always send you Professor Hardy's email address and you can ask him more questions. Guys, and ladies, if you have any more questions, because I think we need to move on to the second part of the evening. Thank you very much, Professor Hardy. Okay, while Liam is setting up, please remember to take one of these. And if you didn't get a book last week, you can come up to the front and collect the book from me.